No niin, tervetuloa takaisin tänne LOIKKA-webinaariin. Seuraavaksi siirrytään nyt sitten enemmän näihin tuloksiin, mitä on saatu aikaan. Ja tässä vaiheessa nyt sitten kielikin kääntyy toiselle kotimaiselle eli englanniksi. Ja chattiin tosissaan voi edelleen laittaa kysymyksiä. Kysymyksiä voi laittaa myös suomeksi meidän kansainvälisille esiintyjille. Ja tässä nyt sitten kysyessä niin koitan simultaanisesti sitten tulkata näitä kysymyksiä, suomenkielisiä kysymyksiä englanniksi, mutta tietysti englanninkielisiä kysymyksiä kannattaa myös laittaa. Mutta eli seuraavaksi siis for our next part of this seminar or webinar, we're talking about the actual results that we've gotten. Well, I haven't gotten any results, but anyway. First up, we have Antonova and Ekaterina Illarionova. I hope I said that right. Talking about the early strength development of low carbon concrete. Go ahead.
Hello, my name is Antonova and I'm postdoctoral researcher at Aalto-yliopisto, and currently I'm involved in the sub-project 1 of LOIKKA project, which is concentrated on early strength development of low carbon concretes. So first of all, I will give a short introduction before we will present our results. And I would like to explain the main goal that we're trying to reach in this sub-project and the things that we're concentrated in and we're trying to affect. So first of all, one of the options that we're considering in this sub-project to reduce the CO2 emissions of concrete production is a reduction of the cement clinker in the cementitious binders. And main things that we are investigating is the using a supplementary cementitious materials and mainly the slag to substitute the cement clinker. As you can see on the graph, we can save some equivalent amount of CO2 emissions by using binders with the higher amount of slag there. One problem with the concrete that has a lot of slag in their content, I'm sorry about some shifts in the text there on the graph, is that when you have a lot of slag, the compressive strength at the early ages is reduced comparing to, for example, SEM 2B. And this is actually postponing the whole timetable of the construction site, and for example, the frameworks will be removed later at the later ages. So our aim is to actually accelerate the early strength development of the concretes with the cementitious binders that contain high amount of slag to the levels of SEM 2A cements. B cements. So first of all, to understand why we have this decrease in strength, we need to understand the basic of the hydration. So what is happening there exactly? And first I will explain the basic mechanism of hydration of cement clinker and the main steps that are happening there when we're adding the water. So for example, if we consider the cement clinker grain as a brick factory, for example, when we're putting the clinker grain into the water and starting mixing, what is happening, it starts dissolving and producing ions, and the ions can be considered as the bricks. So the brick factory is producing bricks, and the water is actually acting as a warehouse for all these ions there. So at the moment, when we have so many ions in the water that the warehouse, which is the water, cannot accommodate anymore, the logical thing that is happening, the hydrates start forming, and this process is called nucleation, and this is the moment where you start building your brick wall. And so by removing some ions from the water into the hydrates, what is happening, you have more space, and the clinker grain can produce more ions, so dissolve more, produce more bricks. And what is happening further, it's like the balance process between dissolution and formation of hydrates. So the hydrates are growing and growing around our grains. So this is the basic thing that is happening. And by growing, the hydrates, they're kind of with this spiky hydrates, they're like hinging between each other and holding everything together. And this is how we're getting the strength of the concrete. So going to our cementitious binders that we are using, so basically CEM3A and CEM3B. In CEM3A, weight-wise, we have like 40% of slag, and in CEM3B, it's 70% of slag there. By the weight and by the volume, you can see on the bottom, underneath the pictures. So what is happening usually in that kind of cements is that when we're adding the water, clinker grains start dissolving, not the slag. Slag needs the activation with these ions that are produced by the clinker grains. So at the first 15 minutes, nothing is happening much with the slag. So at the moment, when we start forming the hydrates on the clinker grains, there is some spare ions that can actually attack the slag and help it to dissolve. But since the slag has a bit different construction of its crystalline structure, the way how it is behaving further, it's a bit different from the clinker grains. So basically, it's kind of attracting some ions, and they're forming this layer that stops slag from hydration at this very first days. And at the later, like within the first day, it kind of forms this retardation layer that doesn't allow slag to hydrate at some point. So as you can see in the pictures, the more slag we have, the less like the spiky hydrates that can hold everything together are forming within the first day. But the thing is that with the time, something is happening. No one actually knows specifically what is it exactly, but what we observe, like up to 28 days when the compressive strength is getting higher, even in the slag concretes, is that it also starts hydrating. So it's also gives it effect to hold everything together. But the problem is that, it's happening a bit too late to somehow affect effectively the time schedule of the construction site. So the things that we are trying to affect in this sub-project is influence the dissolution of the slag and the nucleation of hydrates on the slag. So it start producing hydrate, it start helping bind everything together. So for that purpose, we need to activate the slag, activate those two mechanisms. And so far, I will just do a small recall of what is happening now, is that we have only slag and a clinker. And in the case of slag, what is happening, it gets this passivation layer in the first days, it's not hydrating, and then the hydration is happening later, at the later days. But what we want to do is we want to do some activational steps, and then do so that the dissolution starts earlier within the first day, and the hydration start growing also within the first days. So for that purpose, what we're doing, we're using two main activation methods. One is a chemical activation, which means that we will add, usually in a liquid state, some chemicals that will produce additional ions in the water that can more aggressively attack slag and force it to dissolve. And also there is another group of chemicals that can help to provide this kind of surfaces for hydrates to grow, and that will affect the nucleation. And another mechanism that we also want to try is a thermal activation. So the idea of thermal activation is that we're providing heat into the system, and this heat is giving energy to the water molecules, and the water molecules already start attacking slag more aggressively, also forcing it to dissolve. So I will explain a bit those activation methods that we use. So first of all, for the thermal activation, we implemented the heating cables, which were casted in the middle of the concrete samples with the cement binders that I mentioned before with a high content of slag. And they were place in kind of this loop pattern, similar to the one that is used for heating concrete in low temperatures, usually during the winter time. Even though it's not that popular right now, maybe. But still, we wanted to try this method because by giving, we can control the amount of power, amount of heat we're giving into the system. And since the size of those samples is pretty large, we cannot put them in a compressive machine. So the measuring methods that we use here are non-destructive and include rebound hammer and ultra-pulse velocity. So when we're using the rebound hammer, we characterize the surface condition of the material, but the ultra-pulse velocity allows us to access the in-depth properties of the concrete that is measured. And also the temperature tracking was implemented to see how the heat is increasing the temperature of the concrete. Is it going too high or not too high? Can we increase the amount of power we're giving to the material? So this is one method that was used, and another one is a chemical activation. So the admixtures, chemicals that we were using, they were added mostly in a liquid form during the mixing time. So one group of the chemicals was added to affect the dissolution, as I already mentioned, and mainly the sodium hydroxide and sodium sulfate were used. And for the to affect the nucleation, the X-seed and calcium carbonates were used. And I would like to pass now the floor to Ekaterina, and she will continue with all the results we achieved within this methods that we used.
Okay. Yeah. My name is Ekaterina Illarionova. I'm a PhD student at Aalto University. And my thesis topic is quite similar to the name of the sub-project 1, early strength development of low carbon concretes, and today I will present the results of our research. And first I would like to start from thermal activation. It is needed, as Anna said, for activation of slag, and as you can see on the picture, we used quite big molds for casting, because one of the reasons for that, we need to place the cables and it needs space. That is why the mold's quite big. The second reason that we needed the methodology which allows us to estimate early strength development in non-standard molds, which have different temperature development due to the different amount of cement which produce different amounts of heat and affects the strength development. So for that purpose, we used rebound hammer and ultrasound pulse velocity. We measured these samples during first 48 hours for early strength development, and also during that time, we measure temperature evolution. So because the rebound hammer characterize mostly the surface and UPV characterize mostly the inner characteristics, as Anna said, we decided to find the relationship between non-destructive methods and destructive methods. For that purpose, we took the samples and measure for them rebound hammer and UPV, and then made correlation with the compressive strength. Since they characterize different surfaces, it was logical to combine them. That is why we combined and measured it with, we estimated early strength development with SONREP method, which takes into account UPV and rebound number. And it shows us the less error. That is why this method was used for further testing, and we estimated early strength development for big cubes with SONREP method. Back to the results, we applied continuously the power and only the power. We applied continuously during a specific time. And as you can see, for SEM3A, even the small amount of power allows us to improve the temperature development of SEM3A comparing with the reference concrete. As the reference concrete, we used SEM2B Oiva cement. And here you can see that even 3 kilowatts hour per cubic meter allows us to shift the temperature to the left. However, if we look at the results of compressive strength, we can see that only the highest amount of power allows us to reach the level of compressive strength of Oiva. Oiva is the second one, dark gray. The biggest improvement occurs at first 24 hours. For SEM3B, we achieved not so good results, but still, in some cases, we applied longer power to the system, 5 hours more, 15 hours in general. And you can see that during first 16 hours, the power apply doesn't allow us to exceed the compressive strength more than 5 megapascals. And we were not able to achieve the level of compressive strength of reference Oiva during the whole measurement time. And also you can see this. I'm sorry, I'm quite slow with the laser point because I need to use my left hand. As you can see, the sharp decrease of the temperature shows that we measured not only the heat development which was produced by hydration process, but also the heat of the supplied power. Further, chemical activation. For chemical activation, we used commercial activators. Okay, I just will change my hands. Exit, calcite-based and alkali-based. They were mixed with SEM3A and SEM3B and tested with standard compressive tests. And we received the results which shows that alkali-based activator demonstrate the best activity for both for SEM3A and SEM3B. And for SEM3A, it even exceeds the results of compressive strength of reference concrete SEM2B. And for SEM3B, we didn't achieve the results of Oiva, but still we could improve the compressive strength 3 times compared to the pure SEM3B. And another both activators, Exit and calcite-based, at early strength development, they didn't allow us somehow to improve the properties because they left almost at the level of the pure concretes. However, at the later ages, after 7th days, the alkaline-based accelerator decreased the strength development, but still it stays at the same level as Oiva. The same was for SEM3B, a bit less, but in general it is quite close to the level of SEM2B. Calcite-based and Exceeds stays at the same level as pure SEM3A and SEM3B. Alkali activation. Somehow to simplify our testing procedure, we used prisms for testing the compressive strength. Also, it allowed us to increase the amount of specimens. For prisms, we used cement paste, and also we measured temperature developments through insulated box, which allowed us to simulate semi-adiabatic conditions. First, we decided to check the reactivity of slag. We replaced the equivalent amount of slag with an inert material, in our case it was quartz, and checked the strength development. As you can see, slag started to react slightly already in 24 hours, what shows us that there is something happened, and since there is no compressive strength gaining in inert material, we can assume that slag reacts. And since we were able quite successful in the case of SEM3A to activate it with thermal activation, it was quite challenging to activate slag in SEM3B. That is why we used sodium hydroxide. We added 1 and 2% of sodium hydroxide, and we can see that 2% were better than 1%, and that is why it was chosen for further experiments. Also, we tried 3% of sodium hydroxide, but the workability of the cement paste was so slow, and it affects the repeatability of the experiments. To increase the dissolution of the slag, we also added sodium sulfate, and we tried to add exit to add additional nucleation sites. And the results showed that SEM3B with addition of sodium sulfate and exits showed the best results of compressive strength. The same pattern we can see in the temperature development. So sodium sulfate with exits, this dotted line, showed the highest temperature development among the activated cement pastes. But however, correlation between the temperature development and compressive strength is quite low, because as you can see at 48 hours, for example, the pure SEM3B demonstrates the highest temperature development, but still, if we check at the compressive strength in 2 days, it demonstrates the lowest results of compressive strength. So based on the mentioned above results, we can make two main conclusions: that SEM3A is possible to accelerate with the thermal activation and chemical activation, since for SEM3B, thermal activation is not so efficient, and chemical activation supposed to be the main solution for the research, the main solution for the increasing of slag activation, what our further research is going to apply. This is all for my case, and I'm glad to invite my colleague.
Before we move on to our next presenter, we have a question here on the chat.
Okay.
What was the calcium carbonate accelerator?
Let me return back to the...
I will answer this question. Yeah, okay. I will answer this question. So basically, we received it as a prototype from the company. So we did a chemical analysis and, well, saw that there is mostly calcium there. So this is why we called it calcine-based. But we don't know the exact composition and the structure, what grains are there exactly. We just know like the chemical composition of it. So that's pretty much it.
Thank you, Anna. And then what kind of a chemical is this Exceed?
It's also commercial. It was provided as commercial, and it contains this Exceeds as nucleation parts. Probably, if I'm wrong, please, Anna, help me.
Maybe. Yeah, well, I'll comment on this as well. So basically, this is a small seeds of CSH. CSH is one of the main hydrates in the cementitious materials. So it's kind of, you already give some seeds that other hydrates can grow on straight away. So it's not only the cement clinker grains that hydrates are growing on, but also already on this seeds that we're implementing into the matrix.
Okay, thank you again. Alrighty, and then, now we're pouring in with questions. Okay, we'll ask some of these right now, and then we have time later on at 15:15. We have the closing conversation where all of these questions that you've put on the chat will be answered. So don't worry. Alrighty, let's move on. I think we have a time for a few questions still. Which can you elaborate the used mix design in your tests? How much, for example, of the CEM 3B did you use, and what was the water cement ratio?
The water cement ratio was 0.45, and the amount of CEM 3B, I'm trying to remember because we casted it quite a long time ago.
No worries, you can check it up and then we can return to that.
Okay, yeah, probably we will check. Yeah, it is better.
We can return to that. Which cement factory made the cements?
Fincementti, I suppose.
Fincementti from Parainen, yes. Okay.
Yeah.
Okay. I had a whisper in my ear right here.
Okay.